Hey folks, as usual, for the last video of this lesson, we're going to do just a couple of practice problems, so we'll get started. Impulse and momentum problems can be kind of diverse, but they're all, I don't know, they're going to look similar to mostly other types of problems that you've been used to with Newton's second law or work. I tried to pick two that were fairly unique, as a lot of them are a little bit more predictable. So number one is a very general setup that can get more specific. So we have some values in here. A puck has a momentum and then receives an impulse, and then we know the velocity of the puck afterwards. Now, the equation that you have in your equation sheet is J is equal to force or average force times time, and that is equal to change in momentum. And so the issue with a momentum and impulse problem is deciding like how to use that equation. Rarely, if ever, do I use J, but I'm about to in this problem. I usually choose the force times time and the delta P. What you want to take note of is that this value here, the momentum, is part of delta P. The impulse is given to you, and then you get a final velocity, and velocity is related to momentum also. So I'm going to basically choose these two parts of this equation to solve this problem. So the way I'm going to approach it is impulse equals change in momentum, which is final momentum minus initial momentum. And so that's what I'm going to use to solve it. I have to pay close attention to direction, and so I'm going to fill in whatever I can. The impulse is 250 Newton seconds west. Now I'm realizing that last video I forgot to talk about the units of impulse, but since it's force times time, it's Newton seconds, and during class I'll go over the fact that that's the same thing as kilogram meters per second. Sorry about that. The impulse is west. The initial momentum was east. Now I'm going to set east as positive because that's kind of typical. And so anytime it says west, I have to apply a negative sign to that. So the impulse is negative 250. The final momentum, well, I have the final velocity, and the question says, what is the mass of the puck? So instead of leaving that as final momentum, I'm going to put in mass times negative 5, because that's what the momentum is, mass times velocity, and the velocity is going to be 5 in the west direction. Minus the initial velocity, which is a positive 190, so minus 190. Just take note of all the signs. Make sure you ask questions if you don't understand when you get back in class, or right away if you're in class watching this now. The negative in front of the 250 and the 5, those are because they are in the west direction. The minus sign in front of the 190 is not tied to the 190. It's just the definition of change in momentum requires that you subtract the initial momentum. So then you work your magic with algebra, and you get a mass of 12 kilograms. So this is not a hockey puck. This is maybe a puck of like ice that someone has created. Anyway, all right, next problem is a lot more involved, and will take double the time probably. A ball is dropped from rest from a height of 2 meters. The ground delivers a force on the ball that's described by the force on the graph. Calculate the maximum height of the ball after the first bounce. So at this point in physics, you have kinematics, forces, energy, and now momentum. And so what happens to this ball, it's dropped and it hits the ground. When it hits the ground pushes it up, and then it flies back up in the air. When something is in the air, you can apply kinematics or energy to it. When something is being pushed by the floor, you can either apply work, net force, or impulse to it. So learning like which concepts go with which scenarios is pretty important. So let's analyze the drop first. This is actually the trickiest part. Now, it starts 2 meters off the ground, and then it lands on the ground. That means that the system begins with initial gravitational potential energy, and then by the time it gets to the ground, it ends with kinetic energy. So we are only describing the time from the release of the ball, the moment it starts to hit the floor. And I can solve for the speed with which it hits the floor. So 10 times 2 equals 1/2 v squared. And so that speed is 6.3 meters per second. Now we have to take pause here because this ball was dropped. So it was moving downward. That means that the velocity is going to be negative 6.3 meters per second. So you always have to be paying attention to vectors. The AP exam is not going to probably do something like that to you, where you have to like insert the negative, but I will. So just pay attention. Okay, so that's the drop. Now, why do I need to know the speed or velocity when it hits the floor? I need to know that because there's going to be an impulse that's going to change the momentum of this ball. So the floor is going to deliver an impulse, and I have a graph over here. So I'm going to find the area under the graph, and that's a triangle. So I'm going to do 1/2 base times height, which is 1/2, okay, 80 milliseconds, so that's 0.08 seconds. And then the maximum force is 60 newtons. So with impulse, do be careful. We use the millisecond unit a lot because collisions don't take a lot of time. That means the impulse is a positive 2.4 Newton seconds. Okay, I'm not entirely done with the floor yet, so I'm going to continue on and say that the impulse is equal to the change in momentum. And so here's where this problem is similar to the one above it, that I know the amount of impulse and I can use it to figure out the momentum of the ball when it's leaving the floor. So in general, when you're doing problems involving multiple concepts, you would only use momentum when there's some sort of collision or interaction between objects. This like drop of the ball, you could use momentum, but it wouldn't be any easier than using energy. In fact, energy would be much easier than using momentum. Okay, so what can I do? I can say the impulse is positive 2.4. The final momentum is going to be the mass of the ball times the final velocity. And then the initial momentum is going to be the mass of the ball times the initial speed. So that's going to be the velocity when it hit the floor. So that negative 6.3 was the initial velocity of the ball when it started to hit the floor. And so when you calculate everything, you get this final velocity of positive 3.3 meters per second. And unbelievably, we are not done yet because we have found only as far as how fast is it going when it leaves the ground. So we covered the drop. We know how fast it was hitting the floor. We now covered the floor. We know the impulse delivered and the velocity of the ball after it leaves the floor. Now I can finally find the max height. Okay. And so it leaves the ground with kinetic energy, and it reaches its maximum height having only gravitational energy. So 1/2 3.3 squared equals 10 times that maximum height. And so this new maximum height is 0.54 meters. All right, and that is actually the answer to the question. And so this is a very involved question that I really wanted to include just to show you that you know a lot of physics right now, and now the additional task in physics is to figure out which physics concepts apply in what situations. Good luck.